classical mechanics, we are still working on Lagrangian mechanics problems. And, from my perspective, I need to do like the best problems. There are so many problems I could do this forever, but I want to do this problem because I've seen it multiple times and because we can use this to talk about conserved quantities, and that's what we're going to do. So here's the situation. I have a table, and there's a hole in the middle, and it's a frictionless table. Of course, we always have frictionless tables. You can get frictionless tables at the physics store. Just order them from the physics store. So I have a mass M1 and a string's connected to it, goes through the hole, and then there's a mass M2 hanging down below. This mass can only move this way, and this mass can stay on the plane. Okay, so you got to think now, the first question always, how many degrees of freedom, how many generalized coordinates? There's one way to do this, right? I could say, well, how many degrees of freedom period are there, and then how many constraints do we have? So let's do it that way. So in this case, you could say this mass could be anywhere. Okay, so that mass can be anywhere, so it has 3 degrees. This mass could be anywhere, that's 3 degrees. So that's 6 coordinates. I need 6 coordinates to really describe the location of those things. But this mass is constrained in 2 ways. So -2, because it can't go in the x direction. This is the x, and that's z direction, we'll call that. It can't go in the x direction. It can't go in the y direction, so it's -2. So I only need 1 coordinate for that. Up here, this cannot go in the z direction, so that's -1. So that means 1, 2, 3. 3 coordinates. But there's another constraint, right? Because this string is a constraint. This string says that as this thing moves that way, this thing moves that way too. So the distance between these is set. So that's another -1. So now I have 1, 1. I have 2 degrees of freedom. Now I get to pick what I want for those 2 degrees of freedom. I could pick the x coordinate of this and the z coordinate of that. I'm not going to do that, okay? But I could. But you can see if I have something moving in a flat plane and it's about that center right there, and I definitely need that distance right there, I could use polar coordinates for that coordinate system. And then I can use, I can actually get this in another way. So here I kind of have a little line. Let's call that the angle theta, and let's call that the distance r. So with that, those are the only 2 coordinates I need. Because if this is some constant string length, then and this is r, this is the leftover distance. So let's just call that z2 right there. Now, but z2 is confined, right? It's constrained. So I'll go ahead and say z2 plus r, actually I'm going to say minus z2, plus r is equal to some constant c. So I put minus because if I call this the xy plane, that's a negative z value. You could do it either way. Just make sure that you stick with your coordinate system that you pick. So I'm going to pick that's positive z, so this has a minus z value. So that means that these two, the negative of this plus r is a constant. Okay, so we have our generalized coordinates. I'm going to erase the picture. So, no, I'm not. I'm going to write once you have your coordinates, you want to write your kinetic energy terms. So to do that, you need to get you need Cartesian coordinates so you can take derivatives and apply them in the kinetic energy formula. That's what we're going to do. So let's go ahead and write those down. So I have z, I'll put minus z2 plus r is equal to a constant. That's going to be important. And then I have the x and y coordinates of this. So if I call this the x direction, the x value, we'll call that x1, is going to be r cosine theta. The y value, y1, is r sine theta. So those are my main things that I have there. They're all in terms of just 2 variables, right? I wrote z, but this is really the important one. And in fact, I could solve that for z, and I'll put it right down here. Z2, if I add that to both sides, is equal to r minus c. So these are my 3 coordinates I need for my kinetic energy. So let's go ahead and write down the kinetic energy term. And I'm going to erase all this. We'll come back to it, but it's just too big of a picture. T, the kinetic energy, is 1/2 m2, that's the hanging mass, times z2 dot squared. Right? It's velocity in the z direction. Only moves in the z direction. Plus 1/2 m1 times x1 dot squared plus y1 dot squared. That's what I need to do. So I need to get z2 dot, I need to get x1 dot, I need to get y1 dot. Here's z2, so if I take the derivative of that, z2 dot is going to be r dot minus c. Well, that's fine, because r dot is what we wanted anyway. Okay, so now I can get rid of the z dot, but let's just go ahead. Let's take the derivative of x1 dot. The derivative of x1. So here, r and theta are both variables. So I get r dot cosine theta minus r theta dot sine theta. So remember, the product rule still works, right? So when I take the derivative right here, I take the derivative of r with respect to time times cosine theta, plus the derivative of cosine theta with respect to time, which is negative sine theta, and then I take the derivative of the inside, which is theta, and that's where I get the theta dot. Okay. Now I'll do the same thing for y dot. Y1 dot is going to be r dot sine theta plus r theta dot cosine theta. And it's plus because I take the derivative of sine, I get cosine dot negative sine. Okay, so this one's going to be easy to plug in, and in fact, I'm just going to use the magic of the eraser to put that in there. So z2 dot squared is r dot squared, so I'm just going to put that as r dot squared. And I like to do it in a systematic way so that we don't have to worry about, any tricks or anything like that. But now we have to do the hard work of squaring this, squaring that, and adding them together so we can put them in here. So if I square this, I'll write it two separate. X1 dot is going to be r dot squared cosine squared theta. And you could skip a lot of steps if you think things through, but it's better not to make a mistake. Now I'm going to get, let's put this term in here, plus r squared theta dot squared sine squared theta. Now I'm going to have twice the cross term, so minus 2 r dot r theta dot sine theta cosine theta. Now over here I'll do y1 dot squared, so I get this r dot squared sine squared theta plus r squared theta dot squared cosine squared theta, and then the cross term I get plus 2 r dot r theta dot sine theta cosine theta. And maybe you can see what's going to happen. It's not a big mystery here, right? So when I add these two things together, here I have a negative 2 r dot r blah 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 blah, and I have a plus 2 r dot blah 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 blah, and they cancel. And then down here I have r squared theta dot squared sine squared theta, r squared theta dot squared cosine squared theta. I can factor out the r squared theta dot squared and get sine squared plus cosine squared, which is 1. So those go away. And the same thing over here, I can factor out the r dot. So my whole kinetic energy term, 1/2 m2 r dot squared, that's that term, plus 1/2 m1, and then x1 dot squared plus y1 dot squared is going to be equal to r dot squared plus r squared theta dot squared. Okay, so that's pretty nice, and you could have said that, oh, it's polar coordinates. I know the kinetic energy and polar coordinates, and that's fine, but you can't always expect yourself to memorize all that stuff, so this is useful to do. Okay. Now, what about u? What about u? So u is just going to be, if we call the top of the table y equals 0, z equals 0, then that has no potential energy, and it's just the potential energy down below, which is going to be m2 g z2. Okay, now remember z2 is negative, so the potential energy is negative. That's fine, but I don't want the potential energy in terms of z2. It's not one of my generalized coordinates, so I have to go back over here and put in r minus c. This is going to be m2g r minus m2g c, and c is just a constant. So if we put all that together, I have my Lagrangian. I'm going to write it up top so we can use it more than one time. L is going to be the kinetic energy term, 1/2 m2 r dot squared plus 1/2 m1 r dot squared plus r squared theta dot squared, and then minus the potential, which is this. So minus m2 gr plus m2 gc. Now, I can do something here. I have a 1/2 m2 r dot squared. I have a 1/2 m1 r dot squared. So just to make it a little bit easier, m1 and m2 are constants, right? So I'm actually just going to erase that. I'm going to write this as m1 plus m2 r dot squared plus 1/2 m1. It just looks a little bit better, right? Because that's just a constant term. It doesn't matter whichever way you do it, it's fine. Okay, so now we have a Lagrangian with two generalized coordinates. That means that we're going to get two Euler Lagrange equations. Let's do theta first. So I have the partial of L with respect to theta minus the derivative with respect to time of the partial of L with respect to theta dot equals 0. So let's start with this, the partial of L with respect to theta. Okay, I scanned through here, I'm looking for thetas. There's a theta dot, but that's not theta. So there is none, so 0. That's important. That's really important, we'll come back to that. Over here, I get the partial of L with respect to theta dot. I can do that. Scanning, okay, that's the only one. So I have a power rule. I bring that down. I have m1 r squared theta dot. Okay. Now, we could take the time derivative, and you get two terms. Okay. But for right now, I want to point out something very important. Since the time derivative of this is equal to 0, that means that this is equal to a constant time term. And in fact, we call this the generalized momentum. And I'm going to use L. So it's not momentum, right? Because it doesn't have to, it could be momentum, but it doesn't have to be momentum. It's generalized. It's one of the coordinates. Okay. This is generalized force. But we don't need to get into that. But this is important right here because this says that this term is constant. So even though theta dot can change and r can change, the combination of them has to be constant. And we're going to call that the angular momentum, lowercase l, because we already used capital L up there. Okay. So let's put that over here because it's kind of important. M1 r squared theta dot equals L, and we'll put a box around it to protect it. Now we can go on to the other coordinate, r. So the partial of L with respect to r minus the time derivative of the partial of L with respect to r dot is equal to 0. So let's just do this part first. The partial of L with respect to r. Scanning. That's an r dot, doesn't count. There's an r, so let's take the partial of that with respect to r. What's the power rule? So I get m1 r theta dot squared. Okay, looking for more r's. There's an r. So I get minus m2 g. And that term's just constant, so there's no derivatives there. That's good. Okay, now we're going to do the partial of L with respect to r dot. So I'm scanning up here. There's an r dot. So I can bring that down. The power 1/2 m1 plus m2. The 2's cancel. R dot. And there's no other r terms. So now I can take the derivative of that. The derivative with respect to time of the partial of L with respect to r dot is just going to be m1 plus m2 r double dot. Now, this minus that 0, so this has to be equal to that. So let's write that as an equation. I can just write this as equals m1 plus m2 r double dot. Okay, now, I mean, we have a couple options here, right? I'm pretty much done if I solve this for r double dot. That's, if we think about numerical calculations. How do we proceed with the numerical calculation? Well, if I have that second derivative, I can use that to find out things in the future. And this equation only depends on the second derivative of r. There's no second derivatives of theta, because remember that was 0. So I could solve for this, and let's go ahead and do that. I'm going to write this as r double dot is going to be equal to m1 r theta dot squared minus m2 g over m1 plus m2. Okay, so I have my two equations that are really important right there. It's possible to get this in terms of this, right? Because if I take this term right here and multiply, divide both sides by r, which I could do, I get this term. Oh, and I have to multiply by theta. I could get this in terms of L. I'm not gonna, though, okay? Because I want to just model the whole situation. So again, how do we model this numerically? Because this isn't a simple equation to solve. If I could solve this for theta dot and put it in there, and I would get an equation that only depends on r, and that's fine, okay? But I'm going to just do this anyway. Well, I think I'm missing an r dot. Did I miss an r dot? No. No, I think it's okay. The partial of L, oh, it would be in here. Let's go ahead and do that. Let's go ahead and take the derivative of this. No, because I will get two terms. It will be useful. So I'm going to take the derivative of this with respect to time instead of equal to 0. So I get m1 2 r dot theta dot. That's the derivative of r with respect to time. And then I have to take the derivative of that. So plus m1 r squared theta double dot equals 0. So I do get theta double dot as a function of time this way. So I can solve this. The m1's cancel, and I get theta double dot is negative 2 r dot theta dot divided by r squared. So negative 2 r dot theta dot over r. So now I have theta double dot, I have r double dot. I can now model the whole situation. So again, my normal numerical recipes, which I've gone over so many times, is that I can say r2 dot is r1 dot plus r double dot delta t. By breaking it into small time intervals, that assumes that r double dot is constant over that time interval. Theta 2 dot, and that's r dot at the end of the time interval, and that's the beginning. Theta 1 dot plus theta double dot delta t, and then I can update the positions. R2, R1 plus R2 dot delta t, and theta 2, theta 1 plus theta 2 dot delta t. Okay, so we can break that into short time intervals and we can make everything happen. We're going to need some numerical values, but let's just make that up as we go. So let's go ahead and model this in Python. And we're going to make a visual module, which would be super nice, right? Because we can see how everything moves. And I'm going to try to make it as realistic as possible. So jumping over to Web v Python. And then I can show that angular momentum is conserved. And that's my goal. Okay, so the first thing I'm going to do is start with some constants. G equals 9.8. And again, I'm not, if I was doing a normal numerical calculation, I would use G as a vector. But I'm not going to because I'm thinking right now that I want to switch. I'm going to keep it the way it is. But I would use G as a vector because I would calculate things with G as a vector. But here I'm using G as a scalar value in all my calculations. I need the constant length of the string. So let's make this width. I'll call it WW. No, let's call it S. That's the size of the table. It's going to be, let's make it a meter by a meter. And then my string will be, let's say, a meter. So C is 1 meter. I just picked some values. Okay. Now I need the masses, the two masses. Let's just say M1 is 0.1, M2 is 0.1. We can change those later. I need my initial values for R dot, theta, theta dot. So R, let's just say r is equal to 0.5, theta is equal to 0, r dot is going to be 0. I'm just picking something. 0, and theta dot is equal to 2. I'm just picking, right? If you don't have interesting things there, if I don't have an angular velocity, it's just going to slide, and it wouldn't be very interesting. Okay. T equals 0, dt equals 0.001. Let's make it super small just so it works. Okay, now what I'm going to do is I'm going to build my table. I need a table. I need mass 1. I need mass 2. I need strings. I need a hole. So I have a lot of stuff to build. Let's just build a table. It's going to be a box. The position is going to be the origin. The size is going to be a vector s, and then zs. That was the other one. So let's say the z is s over 20. Let's just see what that looks like. It'll just look like a box. Okay, let's see how. It's kind of thick. Let's make that thinner. S divided by 50. It doesn't really matter. It's just drawing, right? That looks pretty good. I'm going to put a hole there, and the hole is just going to be a cylinder. So hole is equal to cylinder. Position is going to be the vector. Position is the vector 0, 0, 0. The axis is the direction. I'm going to put that in the negative z direction. Okay, so that the hole will extend down through. Actually, no. I'm going to have to extend it up a little bit. So the axis is going to be equal to vector 0, 0, 0, 0. S over 50 is the length. So let's call that h. So I can put this as h. So the axis of this is going to have to be h. Let's say 1.05 times h, so it stands up. But that means that I need to put this down. Negative 1.05 times h divided by 2. Right, so I'm going to scooch it down. And then the radius is going to be the size of the hole. Radius equals 0.01. Let's just run it and see what happens. I'm going to change it to black just so it looks cool. But you won't even be able to see it. Okay, let's put the color at black. Color equals color dot black. You don't need the hole. Look at that. It's not really a hole. It's just a cylinder. Okay. Great. So now I have my table. Let's make mass 1. M1 is going to be on the table. So I already know theta, right? So I'm going to use those polar coordinates. It's a sphere. It could be a cylinder, but I'm going to make it a sphere. It'll be fine. The position is going to be equal to r times vector cosine theta, sine theta, 0. Radius is going to be equal to 0.02. Color equals color dot yellow. Make trail equals true. Okay. And again, so when you create things, run it just to make sure things are working the way you expect. So there it is right there. I put r as too large. So it's right at the edge of the table. Let's make r a little bit smaller. See how I'm adjusting things. So let's make it 0.3. Okay, that's good. And I'm going to change this constant while I'm thinking about it to 0.6 because I don't want my bottom thing hanging down too low. Okay, now in order to calculate, I could have calculated x2 and y2 and then put it in there, and we will do that. But let's calculate z2. It's going to be equal to, looking at my equation over here, z2, I erased it. Okay, well z2 was negative c plus r. I think that's right. Okay, so now M2 is a sphere. Position is going to be equal to vector 0, 0, z2. See? Radius is 0.02. Color is color.cyan. Okay, so there's my table, and if we look underneath it, there's my hanging mass. Now let's make a string to connect everything. I'm trying to think what color I should make the string. I'm gonna make it red. Okay, so the string is gonna be actually two pieces, right? I have a string going from mass 2 to the whole, and from the whole to mass 2, from the whole to mass 2. Okay, so let's say string 1 is going to be equal to a cylinder. The position is going to be, I actually want it above the top of the table, right? Because the center of the table is at 0, and I want it at the top of the table. So its position is going to be vector 0, 0, h over 2. So I'm going to shift it up a little bit. Then the axis is going to be equal to, it's going to go from there to mass 2, so it's going to be, mass 1. Mass 1.pos minus vector 0, 0, h over 2. And then the radius, let's put the radius at 0.005, color equals color.red. Let's just see what happens. This is the art part of physics. Okay, so something happened there. Oh, you know what? So the problem is that my cylinder, my ball is in the table. So it's actually a diagonal line down. That's fine. I can just shift my ball up h over 2. It's still down. Why is it down? Okay, let's see. So it's from there to the center of the ball. Why is that? Oh, no. So that's h over 2 for the string, and the ball is at h over 2. I can just raise that up a little bit. Or I can make the string thicker. That's a good way to cheat. And that'll look fine. Okay, good enough. Now I'm going to draw the string from the hole to the bottom. Now this one I can actually, I know it's just going up and down, so I don't have to worry about, I can make it extend into the hole. String 2 equals cylinder. Position equals vector 0, 0, 0. Axis equals, it's going to go from 0, 0, 0 to mass 2, so axis is just going to be mass 2.pos. And then the radius is 0.01, color equals color.red. Okay. So there's my top, there's my bottom. You know, just for fun, let's just do this. It makes things go slower, but I think it will help. So the table, I'm going to make opacity equals 0.5. So it's a clear glass table. Oh, it didn't like that. There it goes. So you can see the other mass down below it. Okay. Whew, we drew our stuff. Now we need to start making our calculations and animating our things. Okay. So down here, let's run this for 5 seconds. While t is less than 5, rate 1,000. And we can change that. But remember, I have a time step of 1/1000th of a second. So I need a rate of 1,000 times per second to make it run in real time. We don't have to be in real time. Now I'm going to calculate r double dot, r d d d d d dot. That's what I call dot. It's got 2 d's. And I'm looking up here. It's m1. Oh, it's at. Ooh, I just realized I did something. Did you realize what I did? Let's call this m1 and m2. m1 times r times theta dot squared minus m2 times g, and all of that divided by m1 plus m2. Now let's calculate theta double dot. I'm looking at my equation. It's -2 times r dot times theta dot divided by r squared. Oh. Divided by r. Yeah, just that one term. Okay. So now I can update r dot equals r dot plus r double dot times dt, theta dot equals theta dot plus theta dot double dot times dt. Now I can update r equals r plus r dot times dt, theta equals theta plus theta dot times dt. Okay, now what I need to do is to calculate my actual variables x1, x2, and z2. x1, y1, and z2. So x1 is going to be r times cosine theta. y1 is r times sine theta. And I'm going to need this to draw things. z2 is negative c so it's going to be negative z plus r. Did I do that wrong? So negative z2 plus r equals c. So it's going to be r minus c, which I got wrong up here. R minus c. Okay. Now I can draw my thing. So let's move mass 1. m1.pos is equal to vector x1, y1, and then I had that little bump up in the z direction, so h over 2. m2.pos is vector 0, 0, z2. And now I need to move the strings. So string 1.pos I don't need to change, I just need to change the axis. So string 1.axis equals m1.pos minus vector 0, 0, h over 2. And then string 2, did I do string 2? Yeah, string 2 dot axis is just going to be equal to mass 2.pos, right? So just go straight down. Now I need to update time, t equals t plus dt, and let's see what damage we did and if it actually works. If it does, yay. If it doesn't, fix it. Okay. I'm pretty happy. First try. Okay, now what I want to do is to plot the angular momentum as a function of time. I said it should be constant. Let's see if it's constant. And then I'll do one more thing. I know it's already long, but whatever. You don't have to watch the whole video. If you need to go do something, you go. Okay. I want to plot the angular momentum as a function of time to see if it's conserved. And then I want to set up the initial conditions for a stable circular orbit. Okay, so up here, let's make a graph. G1 equals graph. I'm not going to give it a title, but the X title, you got to spell it right, it's going to be equal to time in seconds. The Y title is, I'll write that as L. And it would have units of, I guess, kilograms, meters squared per second squared. Is that right? Per second. I think that's right. Width 400, height 200, and then F1 is G curve, color equals color.blue. Now I need to calculate that, and I don't want to call angular momentum L or lowercase l because I don't like that. Let's call it A. I'm going to call it A for angular momentum. I know that's bad, but I don't like L, lowercase l in Python. So down here, I'm going to calculate it. Let's calculate it after this. Doesn't really matter. A equals, and I can look over here. What did I say it was? It was m1 r squared theta dot. So it's just going to be m1 times what's r squared times theta dot. Let's just plot that. F1 dot plot TA. Okay, so you can see angular momentum is not conserved. Except that it kind of is, right? It kind of is, because look at these values right here. I'm going from 15 to 18. So let's just set this. Why is that times 10 to the third? Or is it negative third? So it's really tiny. Okay, that's good. So it's going to be 0.01. It's because it's so small. So let's set the minimum value to 0.01 and the maximum to 0.02. And let's just see what that looks like. If it looks better. Because it's not constant. Okay. So y min equals 0.01. Y max equals 0.02. Oops. Okay, so it looks a lot better. It's not completely conserved. We can still kind of fix that. Maybe, you know, let's go to y min is 0. Y min is 0. There. It looks a lot better. Okay. I think we could make a shorter time interval. That would fix this a little bit. I would think about why it's not completely conserved, but it's not terrible either. Okay, one last thing. What about a circular orbit? So let's switch to the board for a second. So what if I want to have a circular orbit? A circular orbit is where r double dot is, or r dot 0, right? Because it's not moving out, staying at a constant r, so r is constant. So let's just say that r dot is constant, so r double dot is 0, r dot is 0 too. So I could just set this up and solve for theta dot. That's what I'm going to do. So I got to pick a value for r, but that's fine. So let's just solve this. R double dot is 0, so I get m1r theta dot squared equals m2g. And in fact, this is the centripetal force. Wait, is that right? R omega squared. Yeah, it is. Mass times r times omega squared, and that's the gravitational force hanging down. That's the tension in the string if it's not accelerating up or down. So let's solve this for theta dot. So theta dot is going to be equal to the square root of m2g over m1r. So if I pick a value for r, I can pick a value for theta dot, and then that should be a circular orbit. Let's see if it is. Okay, up here. So I have a value for r right there. So theta dot right here, I'm just going to calculate this as the square root of, what did I just say? m2 times g divided by m1 times r. And let's just see what happens. Well, that worked. Nice, huh? And let's check the angular momentum. It didn't plot that. Oh, that's because I have a different angular momentum. I set the scale. Let's just fix that. Let's just turn off this y max and y min. And you see it looks a lot better now. Okay. Now, there's another problem. I saw a problem in the book, and I'm not going to do it. But it says, what if it's slightly not in a circular orbit? What if you give it a kick? Then you could just do this in a couple different ways. I could do this by solving for this theta dot and giving it an r dot that's not 0. Let's just do that and see what happens. I'm going to give it initial r dot. R dot right here is 0.05. So you see, it's not a circular orbit. It's actually oscillating out back and forth, and that's kind of cool. And again, that looks like constant angular momentum. I think there might be something wrong with my angular momentum, but I'm not 100% sure. That is very constant, 514, so I think it's okay. Okay, there you go. That was a long video. Link to the code down below. Link to, if you're still here, who am I even talking to? But a link to my playlist for all my classical mechanics videos for this semester are down below too. And that's that. I'll talk to you guys later.